Hello. It's fine. Okay. Still not spent. So I hope the screen is visible to you. My PowerPoint, I hope it is visible to you. And if I'm audible, please type your attendance there in the chat box. I will record this attendance also, just for the sake of it. But if there is a genuine problem with some students, I can consider their attendance. Okay. So this was the problem we discussed. We considered this region bounded by the three surfaces. The first surface is infinite cylinder along the z-axis having radius 2. That is, the equation of that infinite cylinder is x squared plus y squared equal to 2. And the bottom of another surface which bounds the considered volume here, the V volume in this divergence theorem is z equal to 0 surface. Z equal to 0 surface, as I discussed, it's a flat surface on xy plane, so that for every surface, that is S1 here, for every point on the surface, z value is 0. And another flat surface we consider is z equal to 3. So we consider a flat surface which intersects the z-axis at 90 degrees, so that for every point on such flat surface, z value is 3. So we have one flat surface on top, another flat surface on bottom, and which cuts the infinite cylinder into this type of cylindrical box, right? So this is the cylindrical box that we consider. And here, in order to verify the divergence theorem, which states that the volume integration of divergence of the vector field, which measures either the net outflow or the net inflow of the vector field over the whole volume, equals the total flux or a measure of the total number of vector field passing through the surface S. The total number of vector field passing, it's a measure of the total number of vector field A passing through the whole enclosed surface, right? So this is what we have to prove. And for that, we start with the left-hand side here. And for the left-hand side, we calculate the divergence of and do this volume integration and all, considering the volume element as dx, dy, and dz, because we are considering Cartesian system, x, y, z coordinate system. And for the right-hand side, we have considered, as we discussed at the very beginning, we have considered three surfaces. One surface S1, another surface S2 here, and another surface S3, which is the curved cylindrical surface. And we have calculated the flux over this surface and found out to be 0. And again, we calculate the flux over this surface and obtain this to be 36 pi. All right. Now our next calculation is to calculate the flux over this curved cylindrical surface, the curved surface over here as represented here. So in order to consider this integration over the curved surface, what we need to find out is we need to find, in order to perform the integration, this is x, this is y, this is z. In order to perform integration over this curved surface, the curved surface here. I can see that. I hope that you can consider a curved surface. So in order to perform a surface integration over this curved surface, we need to find a surface element on the curved surface. Okay, we need to find a surface element on the curved surface. So let's say we consider infinitesimally small element. This, we consider this as a DS3 surface element. And if we write surface element vector DS3, that will be outward unit vector into magnitude of this DS3 that we discussed today. And that will give you an outward unit normal vector, something like this, n cap. All right. So at any point on the curved surface, we can consider the common surface element. So over here on this flat surface, we have said that this surface is lying parallel to the XYZ. So you consider any area element here. You consider any area element here, infinitesimally small area like this. So this can be considered like this to be a small increment along X, and this to be a small increment along Y. So this area element will be this DS2 is area element is dx dy. And similarly over this flat surface, to consider any area element here, this area element, this along this, what I highlighted here, it's your increment along small increment, small segment along x-axis, and this side is equivalent to small segment along y-axis. So this area element is dx dy. So the surface element ds1 is still here also is dx dy. Okay, if it lies on the xy plane, if the surface is parallel to the xy plane, so the surface element you can write it as dx dy. Similarly, if you consider any surface, let's say this is x, this is y, this is z. If you consider any surface, something like this, parallel to the yz plane, this is your yz plane, right? So if you consider any surface parallel to the yz plane, the surface element here in this case will be consider a small infinitesimally small rectangular box. So this segment here is dz, this segment here is dy. See, this axis is y, this axis is z, right? So the area element here in this case will be ds will be dy dz. So accordingly you can choose for a flat surface the area element. All right, now for this curved surface, how are we going to choose the area element ds3? So that I think you can picture from here. So if you draw like a line here where this intersects this and this like this, so this is your x-axis, right? This is your x-axis. So the angle subtended by one edge here, we call it theta, and the angle subtended by the other edge of this small area element, we call it this angle as small increment theta, theta plus d theta. That means the angle here over here will be your d theta. I hope you can understand that. And the radius of this circle, what is the radius of this circle? 2, right? We have considered this area x squared plus y squared equal to 4. So the radius of this circle is 2. So from here to here it is 2. From here to here it is 2. Okay. So you see that in order to consider this area element here, along this, if you look at this, the one I highlighted here, it is along here also. It is along z-axis, isn't it? What I highlighted here is along the z-axis. This edge is small changes along z-axis, or small line segment along the z-axis. So this is dz. That is known to us. But what about this curved surface? There is a curved surface here, a curve, no, not curved surface. There is a curved line here. So for that, let us just look at this way. So I hope you can see that. So this is your dz, and let me redraw it again because I have made it very messy, that picture. So I think I have drawn this cylinder probably for the 4th or the 5th time, I don't remember. So anyway, so we are going to consider a curve, some surface here on the curved surface. So we can see that this will be curved, and but this being the z-axis, so this small segment here, this side will be dz, infinitesimally small segment along the z-axis. But in order to find this segment, the area of this will be, let's say this segment, this curved line is, let's say dl. So area ds3 will be dl into dz. All right, dl into dz. So what is dl? In order to find dl, what we are going to do here is this: we consider it as a, we consider this as a theta, and we consider this as a d theta. That's what we do, right? So if this is the picture, okay, the picture. So the radius here is 2. I hope you can see the picture I redraw here. So this side is your dz. Now, now if you take a tan d theta here, tan d theta, it's like, if you consider to be infinitesimally small segment here, in a small angle approximation, if d theta is very, very small. See, let me redraw something like this. If this angle is large, if this d theta is large, so this angle is quite acute, right? It might be around here, let's say 75 degree or something like that. If this angle is smaller, if d theta is smaller, this angle will now become, let's say this is probably around 85 something. But if you make this angle to be very, 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 very small, something like this, very, very small angle, this d theta is very small angle. So if you consider this angle here or this angle here, they are approximately 90 degree. They are close to 90 degree. Okay. So because of that, you can consider this as a right angle triangle. Right angle triangle. One of the angle, you just assume it as a 90 degree. So this is as 90 degree for a small angle d theta here. This you can consider as a right angle triangle. So if you consider this as a right angle triangle, tan d theta will be opposite. Opposite here is your dl, and adjacent here is the radius of the circle. So opposite is dl, adjacent is 2. Opposite side upon adjacent side, dl upon 2. And there is this thing called Taylor series expansion, which you will probably study in mathematics. Taylor series expansion in physics also, I think Sir Guru will teach you. Taylor series expansion, which says that tan theta is equal to theta minus what is that? Theta square upon 2 factorial plus theta cube upon 3 factorial, something like that. I don't remember exactly. Theta to the power 4 upon 4 factorial. So if this angle theta is small, this is very small. Let's say your theta is 0.01 degree. If your theta is 0.01 degree, what is theta square? Theta square will be 0.001201 degree, right? So if you take theta to be very small, the higher order term, theta square, theta cube, theta 4 term, they will become very, very small. What will be theta cube? Theta cube will be, if you take 0.01 to the power 3, this will be 0.0000001234, this, right? So this theta cube term, theta square term, theta to the power 4 term, they are very small, so they can be negligible for small angle approximation. So there are two things. If this angle is small, you can consider tan theta to be equivalent to theta. And also, if this angle is very small, the angles subtended here, they are very close to 90 degrees. So you can consider that one of them or both of them as a 90 degree, and then you can consider a right angle triangle, and then you can consider a trigonometry, which says that tan d theta is equal to opposite by adjacent. Opposite here is your dl upon adjacent. The side of this triangle is 2, the radius of a circle. Okay, so this is what we do here. Tan d theta is equal to, this is your here as I represented here, dl upon the radius is 2. And for small angular approximation, for small d theta, for small increment here, tan d theta is equal to d theta, because higher order terms are 0, as I explained before, d theta dl upon 2. So your dl is 2 d theta. Then your ds3 will be 2 d theta dz. Right. So that is your surface element ds3. Now, like again from trigonometry, if this is your x-axis, this is your radius r, this is your radius r, this x coordinates over here, x can be written as r cos theta. Okay, if you drop a perpendicular here, this is so messy again. Just for the last time, I will not draw again. X, y, z. So this is the first thing I think we discussed. So I need to take a little bit more time. The rest of the integration, you can do it. So let's say this is your x parallel to x-axis, and let's say this is your this thing, right? So you drop a perpendicular here to this x-axis. So let's say this is 90 degree. So the x coordinate value is this. So this will be, if this is the radius of the circle, and this is your angle theta here, this is your angle theta here. So from this you can write x as r cos theta. And if you drop a perpendicular, this is the y-axis. If you draw a perpendicular, this y here, this is 90 degree. So you can write y as r sine theta. So I hope you are familiar with that. So you can just picture a right angle triangle there, and then you can write x as r cos theta and y as r sine theta. So like this, you write x in terms of theta and y in terms of theta. Here the radius is 2. Instead of r, you just put 2. Okay. So when we do that, and also in order to find the normal to the surface here, so as I have explained before, phi x y z equal to 0, x y z equal to constant is the equation of a surface. So when this is equation of a surface, if you take a gradient of phi, then that will give you the normal. So normal vector to this quantity will be grad of x square plus y square. So you take x square plus grad of x square plus y square gradient. So there should not be any dot product here. So there's a typing mistake, no dot here. Okay, please don't mind. There should not be a dot here in the gradient operation. This is a vector operator and this is scalar, so there should not be any dot here. So that was a typing mistake. And when you take a grad here, this would be like you have to differentiate this with respect to x. So when differentiating this quantity with respect to x, differentiation of x square is 2x, differentiation of y square is 0. So therefore I cap coefficient will be 2x. And here differentiation of this term with respect to y, differentiation of x square is 0, differentiation of y square is 2y. So 2y into j cap, the second term. Now if you differentiate this term with respect to z, differentiation of x with z is 0, y with z is 0, because x and y and z they are independent coordinates. So if you differentiate one coordinate variable with another coordinate variable, they are independent. So it is 0, right? So this is the vector. So once you have a vector, in order to find unit vector, like if you have any vector a here, if you want to find unit vector, what you have to do is simply divide that vector with the magnitude of that vector, then you get a unit vector along that a direction, right? This is how we get a unit vector. Just divide the vector with the magnitude of the vector, then you get that unit vector along that vector direction. So this is what we do. In order to find unit vector, divide the vector with the magnitude of the vector, and this is the vector, and the magnitude is square root of 2x to the power square. So that means 2 square x square. 2 square is 4, 2 square is 4, and then this is what you get. I hope this is okay with you. Now this is your unit vector. So this unit vector at this point, what the unit outward vector is, given by this expression. All right. So at another point over here, another here, the unit outward vector is given by this. The unit outward vector for different point on the curved surface will be different, because the unit outward vector is from vector field, or it depends on the x and y value. So at one point, the unit outward vector may be pointing outward in this direction. At another point, the unit outward vector will be pointing in this direction, depending on the x and y values here. Right. So here, what we have to do here is that we have to perform vector A with ds3 surface element and this unit vector. So you're going to do this product A dot n. So the vector field, we know it. This is the given vector field, and unit vector, as we deduce, it is this. And if you take the product, this is what we are going to get. Okay, now I think the rest of the calculation will simply follow. So if you take this A dot n, we already obtained A dot n as this quantity, that is A dot n is 2x square minus y cube. A dot n is 2x square minus y cube. So 2x square minus y cube, you just put x as 2 cos theta and y as r sine theta, as sorry, radius is 2, so y is 2 sine theta, so like the substitution I discussed. So you just substitute here, and this is algebraic simplification. This is what you will get after this thing, 2 square into 4, 2, and you take 8 as a common, it becomes 16, and this is what you have. And cos square theta, using trigonometry, it is 1 plus cos 2 theta upon 2, and sine cube theta, instead of sine cube theta, you simply write sine square theta into sine theta. So sine square theta is 1 minus cos square theta. So I think you can carefully follow this trigonometric simplification. So here you see that the integration is with respect to the area element is 2 d theta dz, as I discussed, and you have to integrate with d theta first, and then you perform the integration with z. Then if you perform this integration, finally you will get this as 48 pi. So on the right hand side here, you see that we have to the right hand side, the total flux is flux over the surface S1, this bottom surface, flux over the surface S2, the top surface, flux over the curved surface. So you have to sum all of this. The bottom surface flux is 0, the top surface flux is 36 pi, and the curved surface flux is 48 pi. So if you do the summation, this is 84 pi, which is same as what you have already calculated for the left hand side here. The left hand side, if you calculate the volume integration of divergence, this is what you get, 84 pi. Okay, so this is, I think, probably understandable to you. So you follow my lecture again. If you have any problem, any doubt in any of the mathematical steps, you are feel free to ask me to WhatsApp. It's not a problem. Now I think we can go to Stokes theorem. Stokes theorem is for a open surface. See, in this divergence theorem, we are considering a closed surface. We are considering a closed volume, which is bounded by a closed surface. The surface could be spherical, so it could be cylindrical, or it could be any surface, but we are considering a closed surface here in the divergence theorem. But in the Stokes theorem, we are going to consider an open surface. Almost sneezing. So here, what it says here is that if you consider any open surface, two-sided open surface bounded by a closed non-intersecting curve. So non-intersecting curve is what you call a simple closed curve. Like you can consider something like this. So if this is an open surface, this is a curve C, and this curve is like this curve is surrounding a surface S, or you can consider something like this, let's say this is a curved surface. This is a curved surface. Sorry, this is a curve. See, a complete a closed curve. So this is a closed curve, and the surface bounded maybe something like this. So I hope you can see the picture. This is, I don't know if I can show you some other thing. Anyway, I think with an example, it will be more clear to you the surface. So if you have any open two-sided surface, it may not be a flat surface. It can be a curved surface bounded by a simple non-intersecting closed curve. Then if A is a vector field which has a continuous derivative within this surface, then Stokes theorem says that line integration of the vector field over the closed curve. So counterclockwise means clockwise, you know it is rotating like this. Counterclockwise means it is rotating like this. So loop integration of the vector field, line integration of the vector field along that such kind of simple closed curve. If you integrate vector field around this, if you perform vector field integration around this closed curve, then that equals surface integration of the curl of the vector field A. Surface integration of the curl of the vector field A. Curl of the vector field means it measures a rotation of the vector field. So this is the total rotating flux, okay, across this surface, which equals what is that? Line integration of this vector field around this closed curve. This is what Stokes theorem says. So I think this will be